Hi, my name is Hussein Al-Shawi and I'm a mechatronic engineer student at Middlesex University, London. This module is mobile robot and manipulators, and today I'm going to demonstrate the LabVIEW simulation of a generic serial arm manipulator. For this project, I used the Dinivit-Hartenberg parameters to design the robot manipulator. The task itself was to place an object in 3 different shelves and basically pick up the object from one position and place it in 3 different shelves. The only specification given was the height. So that's why only X and Z axis gonna be used. The height was 6 meters, 4 meters, and 2 meters. And the floor is where the object is being picked up from. I've designed the 3 degree of freedom manipulator. As you can see, I'm using 4 joints because one of the joint is only there for demonstrating purposes, and that's the one here. We have a twist angle on it with 1.57 radius, which is rotated in 90 degrees. It's have 0, 0 in length because it's not being used, obviously, and it's so this is the length between one joint and another, and as you can see here, the length is 0, and we have put an offset value as well on it, and the rotation angle is 0 on all of them because it's not needed. They all put as revolute joints. Yes. So that was it for the DH parameters. What we're using here is a polymorphic VI. It's called. It's basically just so the generic arm can be chosen, so the parameters can be chosen for it. We initialize this what it's doing is initializing a 3D object and makes us represent a robotic arm. That's what it just do. We have put the default position here for the joint angles, and all the position is passed on to a loop. The shift register is being used to store the values, so it can be used in the next iteration. So basically, at any time the loop is running, it's gonna take the previous values and put it on into the next iteration every time the loop is running. The forward kinematics is used to get the transform, and then we get the translation vector of the homogeneous transformation matrix here. We use the index here. This index array is to get X and Z location. This tab is to choose between auto and manual jogging. So talking about the manual jogging here, we can see we have the up, down, left, and right, and home button. If you if value is being reached, then it stops. If those values here is being reached, then it makes it stop. So yes, and it's all passed here, all passed into indicators, can be shown in Z and X values, and then from that it creates a transform from the translation. So that's pretty much it for the manual one, and the auto one is used as well, the same button, 5 buttons, but this is for instead of this being for home, up, down, left, and right, this is the auto goes for home, home button, pickup button, shelf 1, shelf 2, shelf 3. So basically it's this is a home, so this is the values for home passed into the read, and this is for the pickup. So what's happening is, let's say a button is being pressed, let's say pickup is being pressed. Okay, press pickup is passed on to array, and then it's converted into an integer, and this is the values it should be located to go to the pickup position. And same goes for shelf 1, shelf 2, shelf 3. So those are the positions. It's to get to there. Okay, moving on this. So this is all in a case structure, obviously. Yeah. Moving forward is we take all these values, and this again is passed into a shift register in this what's it called, loop. So so what it's doing here is basically this, we put another forward kinematics here. The forward kinematics here in this the forward kinematics here is calculating the position and the orientation of the end effector, and make sure that basically it's make sure that it's safe before executing the task. And then from that we get the translation vector, rotation matrix, and the angles. Because we get it in radians, we use this calculation here to get it in degrees. So we take it depending on the values, divided by pi times 180, and then we get it in degrees. And then this is passed to a trajectory block. And this trajectory block is to make sure it's a smooth, can move smoothly in the Cartesian space from the initial to the final position. So it's a very important block that is being used here. And we use info depending on from the speedometer. This have to be used because we have to put the speed to choose the acceleration for the trajectory to move in that Cartesian space. From we make sure that it moves safe and in a controlled speed. So that's why this speedometer as well is there. Okay, and yeah, I forgot. So we choose to get a 4x4 homogeneous transformation matrix gonna be displayed. I will show all this later here. What's gonna happen. So then we move on here and take it into an inverse kinematic block, which is we get the translation along X, Y, and Z. And we make sure that the position of the robot is based on the end effector. So we determine that the position of the robot based on the end effector position and the orientation. So what is basically, we use the DH parameters and the homogeneous transformation matrix to calculate the joint angles and needed to achieve that position. So it calculates the position. Okay, this is a DH parameters, this is the joint angles, this is a button that's being pressed. Okay, where do I need to be? Where do the end effector need to be? So this is what the inverse kinematic plot do. Now obviously we have to update the plot before we visualizing it, and then we use a 3D picture to visualize it. And now here I will show you here. Yeah, here it is. Okay, so so this is this is my visualization here. So if we play it, we can see that here is the manipulator. Like we said, we have a 3 degree of freedom, 3 joints. This is a length that you saw in the DH parameters. So let's say we are in auto now, like we talked about. If we do the pickup button, there it picked up the object. We want to put it, let's say, in shelf 3, which is 600 meter, sorry, is 6 meters, and then in shelf 2, so it picks up the object, put it in shelf 2, which is 4 meters, and put it in shelf 1, which is 2 meters. And here is the speedometer that's calculate the speed in the Cartesian space. So depending on the steps, how much speed you do. So if you take it to maximum 300, then it's gonna go much slower. You see, it goes much slower. If you want to just do shelf 1, it takes long time. So this is a very slow. So if we here, this is a good speed here. You know, this is as well as good. So 100 is pretty good speed. It picks up, place it in the object safely. That's why we don't get any errors, because the blocks have in the trajectory blocks and the inverse kinematics have made sure that the end effectors and the trajectory moving in the Cartesian space is all safe to be moved there. And here, as we can see, we have as well used manual like we showed before. Can be used the manual jogging, up, right, down, left, right. Yeah, it's all good. Yeah. And press home, it goes back to the home position. And you can see here the position of Z and X axis. And yeah, here, like I showed you before, that we get this is the angles. I've converted them from radians from radians to degrees. And we can see here, and this is the joint positions of all the 4 joints that's being used. So you can see this one is not used a lot because that's the one that's just there for demonstrating purposes. And here this is very important because here is our 4x4 homogeneous transformating matrix, and we can see how they change. These 3 here is the translation vectors, those 3 here, and those are the rotation matrix here. By having those, we can get our 4x4 homogeneous transformation matrix. And here we have full information control over the manipulator. Thank you for watching.